De Bock, who is the current president of ISIPTA, and he's going to tell us about choice functions, an axiomatic perspective based on choice functions and desirability. Thank you.
Thanks a lot, Jason. So I've been told that by the very fact that you're attending this event, you should love at least one of two things. The first being imprecise probabilities, and the second being philosophy. So I figured this would be an ideal occasion to talk about something like the meaning of imprecise probabilities. Before I get to that, a bit of background as to where I'm coming from. I'm not from the philosophy. I am a member of the Foundations Lab for Imprecise Probabilities at Ghent University in Belgium. There seems to be okay, are we fine?
Everybody else knows.
Still feedback?
It's on there.
Good to go?
Should be.
Okay, so I'm a member of the Foundations Lab for Imprecise Probabilities at Ghent University in Belgium. There's a whole bunch of us. We all work on various topics within imprecise probabilities. Is there a way I can get this stuff to remove? Because you'll not be able to see all of my slides.
No, we can see it probably.
Yeah, but here, the live people can't.
That's true.
What can't live people see?
Well, whatever.
And alive like me.
Yeah,
Yeah,
you're
okay.
a live
Sorry,
person.
Is somebody, one of you two, better with this?
just drag them to one at a time.
I know, I can't get your. Okay. Let's stop sharing and let's share the whole screen. Maybe that helps. Probably does.
Just need to minimize this here.
The right, yeah.
Where's the mouse
Yeah,
cursor?
that's
Oh
the
gosh.
issue.
Yeah,
So here,
minimize that. Yeah, that should.
give it another go.
Yes.
Yeah, that should work.
Yeah, okay, that should be fine enough. Oops. So, third attempt at this. I am a member of the Foundations Lab for Imprecise Probabilities at Ghent University in Belgium, and there's a whole bunch of us. We work on all sorts of topics within imprecise probabilities. This includes imprecise randomness, which Ghent will be talking about tomorrow at this event, but also Creedle networks, which are Bayesian networks, but then with imprecise probabilities. We've started thinking about how to do quantum mechanics with imprecise probabilities, and we also have lots of expertise on imprecise stochastic processes and in particular imprecise market chains. If you by any chance interested in any of those topics, do get in touch with us. It's not what I'll be talking about today though. Today's talk is situated within our line of research on choice functions. So what those are, and you've already heard a little bit about in the talk of Catherine. I'll be telling you some more about it. Before I do so though, I'd like to acknowledge that when it comes to choice functions, I'm influenced by more than just the people in our group. There's also Teddy Seidenfeld, who's basically the reason why Gert and I started to think about choice functions. And then there's Arthur van Kamp, who used to be a PhD student in our group and is now here in Bristol. he did a PhD on choice functions, and reading that is what got me to not only think about it, but actually start working on it. And then most recently, Catherine also did some very nice, the previous speaker, very nice work on choice functions that also I found very inspiring. So that's what kind of where I'm coming from. And what I intend to do in this talk today, I intend to use these choice functions to shed some new insights, some new perspective into the meaning of imprecise probabilities. So imprecise probabilities, what's an imprecise probability model? Well, for me, that's any model that's able to capture uncertainty about something in a way that's more general than just using one probability measure. But for most of this talk, I'll be focusing on what's perhaps the best known case, which is to just use one set of probabilities. So let's make this quick. Let's think about something that's uncertain. The weather next week, I'm uncertain about that. So I wish to represent that uncertainty with some kind of model. And I may choose to do so by providing a set of probabilities for the weather next week. So then the question is, what does that mean? And I don't want to get too far into this at this point, but there's kind of two ways you might think about it. You might think about this, okay, look, I think the weather next week can actually be described by this one probability measure, just I don't really know which one it is. And so I'm giving you a bunch of them. But there's also people that don't do that and that think that this belief is basically captured by the set itself, like the individual elements of the set don't have any meaning. It's a totally different way of thinking about this. And this matters because depending on how you think about these kind of models, you'll be using them in different ways. For example, you'll be adopting different types of independence, different types of decision making. If, for example, you're thinking about independence and you think about a set of probabilities as being a set of actual probabilities and the elements matter, then you'll be inclined to think about independence in terms of these individual probabilities. You, for example, be imposing that each of them should be independent in kind of the usual way where you factorize. This is called complete independence. But if you think, no, it's the set itself that matters, these individual elements don't have any meaning, you'll have other ways of thinking about independence, and this doesn't make so much sense anymore. The same is true for decision making. If you think about such a set as the individual elements in it really mattering, then you might be inclined to, for example, try and generalize admissibility, and you might, if you have to choose between a set of options, and each of them is like an act, and you associate a utility function with it, then you might be inclined to choose something if it maximizes expected utility with respect to at least one of the probabilities in this set. That would be the admissibility that Catherine was also mentioning about. But if you think that such a set, the set itself matters and not the elements, then you might consider other types of decisions, and so on and so forth. And so what you're left with is you have this whole bunch of imprecise probability models, all different. And then even if you choose to work with sets of probabilities, you have these different meanings you might give to it. And then this all leads to different types of independence, different types of decision making that you may associate with, and you get to kind of pick from all of this. And my aim for today is to provide you with a number of tools that I think can help you make the choice. And those tools, as the title of the talk already gave away, are choice functions and the concept of desirability. Let me start with desirability. So if you're familiar with imprecise probabilities, then this term desirability will ring a bell. And you'll be associating, I presume, this with the concept of desirable gambles. And you'll be thinking of sets of desirable gambles, sets of desirable gamble sets, all these kind of things. Now, I recently discovered, to my own surprise, that that's not needed at all. There's no need at all to think, if you're talking about desirability, to be considering the case of gambles. This whole theory holds much more general, and I'd like to explain that to you. You can apply it to anything. You could, for example, apply it to dogs. You could be considering, so there's some set of things, and that could be the set of all types of dogs. And then what it means for these to be desirable, well, what the term desirable means also is not important for the theory. You get to choose what it means. It might, for example, mean that Jason would consider having that dog. And then we can try and build a model. But this is just one example. We can study the desirability of pizzas as well, no problem. Or we could be studying the desirability of elements of some subset of a vector space, but that's much more boring and not needed for the theory. So I will be sticking with pizzas. So the idea then is, okay, how can we model the desirability of things, or in this case, the desirability of pizzas? Two proposals of how we might model this desirability. The first is we use a set of desirable things, a set of desirable pizzas. This is very simple. So how do I model my uncertainty? I just give a set of pizzas of which I say, look, all the pizzas in there I think are desirable. In this case, let's say that desirable means Arthur would consider eating those pizzas. So this is my model. I'm stating here that I think that Arthur would consider eating pizza pepperoni and pizza meatballs. Maybe it's also some other pizzas that he likes, but no idea. I'm not putting that into my model. This is my model for the desirable pizzas being the pizzas that Arthur would consider eating. So this is the first proposal for modeling the desirability of things. However, this model is nice and simple, but it's not very expressive. Imagine, for example, that I went to a pizza place with Arthur, and that I remember that he had this pizza with olives, and he very much liked that pizza. Now, on the menu of that pizza place, there's two pizzas with olives. And I don't know anymore which one he had. So what I know at this point is that at least one of these two pizzas Arthur finds desirable. I don't know which one. This I cannot model in this simple model that I'm proposing here. I can, however, model it if I move to a more complex model, being a set of desirable sets of things. So now I'm not considering the desirability of things, but the desirability of sets of things. And what I mean by a set of things is desirable is, I mean that at least one of the things in that set is desirable. So here is an example of such a model. It does not include pizzas, it includes sets of pizzas. Each of these sets is desirable. This set only contains pizza pepperoni. I say the set is desirable, that means at least one of the pizzas in the set is desirable. It only contains one, so this is just saying pizza pepperoni is desirable, like before. And similarly, pizza meatballs is desirable. Here is something I couldn't do before. Here I have a set containing two pizzas, and this means the set is desirable because I've put it in my model. That means this set contains at least one desirable pizza. So one of these two pizzas with olives, Arthur finds desirable. I've put that into my model. I can now express that in this language. So a second proposal for a model that allows you to work with desirability. And now on this second type of model, I'd like to propose two axioms, very basic and intuitive ones, I think. The first is the empty set you should never find desirable, because the empty set cannot contain at least one desirable thing, because it doesn't contain them. And then second, if a set is desirable, if a set contains at least one desirable thing, then surely any superset thereof should also include at least one desirable thing. I think that makes perfect sense from this. So these two axioms I'm imposing on this second more complex type of model. Okay, and then we have a result which says that we have these two types of model, a more complex one, the sets of desirable sets of things, and a more simple one, the sets of desirable things. Okay, and it says here that working with one of those complex models is equivalent to working with several of those simple models. It says that, okay, more concretely, for any complex model that satisfies the two axioms, there is a set of simple models such that a set is desirable, it's contained in the complex model, if and only if each of the representing simple models contains at least one thing of the set A that I'm considering. So I call this a representation theorem. It says that this complex model is equivalent to a bunch of working with a bunch of the simple models. And so you can have all the expressive power of the complex model using the simple models, provided that you are fine with using a bunch of them. And that's it. Okay, so this is the basic version of the theory of desirability applied to things. Now you can spice this theory up and build extra things into it. I might want to impose some rationality criteria and build that into my theory. One thing I might want to do is I might want to build in that some things should never be desirable on grounds of rationality. I can, for example, here specify that Pizza Hawaii should, on grounds of rationality, not be desirable. I can tell you that Jason was irrational. A second thing I want to build in is an inference mechanism. I might want to build in some rules, some kind of inference that allows me to infer the desirability of new things from old things. And I'll do this in a very, very general way by using what is called a closure operator. That's a set that's an operator that if you give it a set, gives you a superset back. That's all it is, and it needs to satisfy two very simple properties. It needs to be monotone. So if the set is bigger, then the closure also becomes bigger. And it needs to be idempotent, meaning that if you apply it twice, it's the same as applying it once, which makes sense for a closure operator, for an inference mechanism. Doing it once, all the inferences have been drawn, and so there's no point in doing it again. Okay, so this is the general thing. And just to make it less abstract, in the case of pizzas, we might want to kind of model that if pizza, pepperoni, and mushroom is desirable, and pizza, pepperoni, and peppers is desirable, then that should, by rationality, imply that regular pizza, pepperoni, you also find desirable. We might want to include that as a rule, optional. We might want to include this into our theory. Good, and I can do that with the closure operator. In this case, the closure operator is take a set of things, a set of pizzas, look, does it contain both of these two types of pizzas? If it does, add regular pizza pepperoni to it. That's then the closure. If it does not, don't do anything, just give the same set back. So that's a closure operator that incorporates this mechanism that I might want to include. Okay, so two optional things that we can build into our theory. How do we build these into our theory? Well, we impose some extra actions. The first incorporates this first principle I added. It says that if I have a set that contains at least one desirable thing, and I remove from this set these things that on rational grounds I consider I consider undesirable, then surely what is left still contains at least one desirable thing. That's what this action, for example, here, if I apply the rationality criterion that Jason broke yesterday, then if one of these three is desirable, it should imply that if I remove Pizza Hawaii from it, still there's at least one desirable pizza in there. Okay? And now we want to build in this inference mechanism that we had using this closure operator. This one is a bit more complex. So to explain it, let me break it down with an example. So what this saying is, take a bunch of sets that are desirable. For example, these two sets that each contain, by the model, at least one desirable thing. Okay? And now, consider all possible selections you can make from those. And that means pick a selection is a set you can obtain by picking one thing from each of these sets you started from. So you, for example, pick these two, that's one selection. You consider these two, that selection. These two, that selection, these two, that selection. All possible ways in which you can pick one element from each of these sets you started with. Any selection that you can make in that way, you put it into a set. Okay, so that's this bunch of sets, all these selections. And now it says, for each of these sets, what I do is, I take the closure of that set, of this selection with respect to my inference mechanism, and I pick one element from that closure. And I do that for each of these possible selections that I have. And now the axiom says that if I put all these together, that set should be desirable. So in this particular case, you infer from this that pizza pepperoni, pizza margherita contains at least one desirable. So that's the axiom. Why does that make sense? Well, the reasoning is the following. By definition, each of these two, because they are in the model, contains at least one desirable thing. So there's one selection here that I can make such that all of the elements, all of the things in the selection are desirable. I know this one contains at least one desirable pizza, and this one also does. So if I pick those two, then that selection will contain two desirable pizzas here, right? I just don't know which of the four it is. But okay, there is one for which all the pizzas are desirable. So they are all desirable. By our inference mechanism, the closure of this particular selection will also contain only desirable pizzas. Because this is all desirable, closure is still all desirable, and now I pick one. So for one of these four here, I will have a desirable pizza. And so surely, if I put them all together, then what I end up contains at least one desirable pizza. So this follows purely logically from the inference mechanism that I'm building. This is this second action that I'm imposing additionally. Okay, so these are now the four actions that we're building into this theory, and the last two are optional. If this here is empty and the closure is trivial, then nothing has happened. The cool thing is that with this more general axiomatization, we still have the very same result. We still find that every complex model, every set of desirable sets of things, is representable by a set of the simple models, a set of sets of desirable things. But now, since we have imposed extra axioms on this complex model, we get something extra. We get that each of the simple models also has some extra properties. What we find is that they're compatible with these mechanisms that we've built into our theory. We find that these simple models, which are things that are supposed to contain only desirable things, don't include any of the things that are deemed undesirable by the theory. And these simple models are also closed with respect to our inference mechanism. So this is a more general version of the previous representation theorem that still works for pizzas, dogs, whatever you like. I've imposed no structure on these things. So up to this point. So why am I saying that? And for one, because I think it's very nice that you can do all of these things for dogs and pizzas and so on and so forth. Also because it's connected to imprecise probabilities. You can, for example, apply this machinery to the case where things are gambles, bounded real functions on some possibility space. And in that case, we might want to build into our theory that a gamble that never gives you a positive reward shouldn't be desirable. And do that by choosing this set, A not B. And then I might want to build in the inference mechanism, basically saying that our utility is linear, which then implies that if you have a bunch of gambles that are desirable, any positive linear combination thereof should also be desirable. And I can do that by using these Posey operators, which just starts from a set and then includes all positive linear combinations from that set. And that is a closure operator. Okay. And then it might also make sense to add one more thing, which is that in the model, to me, it makes sense to then also include all gambles that can never make you lose money, but in some cases can make you gain money. If you do that, and you then apply this general result that I have, then you find, as a special case, this correspondence that some of you may be familiar with, that there's this correspondence between coherent sets of desirable sets of gambles and coherent sets of desirable gambles. So that's just for the people that are working with this kind of models, in case you were wondering where's the connection. But it's just a particular case of this whole pizza dot. Okay, but I won't go any further into this. I'd like to move to a different example of this theory, which I found to be quite surprising, which is that the things you're considering could also be preferences. I could be talking about the desirability of preferences, where desirability that means I have that preference. Okay, so the things now are no longer the pizzas or the dogs, but they are preferences between pizzas, or preferences between dogs, or preferences between whatever you like. And I can consider the desirability of these preferences. Okay, and in that particular case, I might want to build into my theory that you should never prefer something over itself. So these preferences you should not be including. You rule those out by rationality. And I think it also makes sense in that case to close your inference with respect to transitivity. So as a closure operator now, you use just the closure with respect to transitivity. If you give a bunch of preferences, you look at all the ones that can be inferred through transitivity, that's the closure. Okay, so for example, say we have these two preferences in a set, then the closure is the one with transitivity. So here, this one should also be preferred to that one because combining those two by transitivity, you get that this preference also holds. So that's the closure. And now I can again apply this general theory I have. Nothing has changed. But the cool thing is now, if I look at this extra power I was having here, the properties of these simple models now say something about these preferences. They say this here says that the preferences in a simple model are irreflexive. And the second one here says that the preferences in a simple model are transitive. So one such simple model is a bunch of preferences satisfying these two principles. That's by definition a strict partial order. So if I apply once more this general theorem I had for the desirability of things, I find that a set of desirable sets of preferences is completely equivalent to a set of strict partial orders. Okay, so at this point, I guess two things could be happening, or maybe both. So the first could be, oh, that's cool. It's nice that you can model preferences between pizzas and dogs. I very much like that. But might also be a reaction that, okay, so you have this equivalence between this complex model and these simple models. And I like the simple models, but really, what is going on with this complex model? Sets of desirable sets of preferences. I know you have an equivalence, but I mean, I can't work with that. It's just over the top. And this could also be a reaction. And I get that. And so, but if you're one of those people, no, okay, some people are not like that.
I think you're doing epistemic utility.
All right. So for the other people, I think I do want something more to convince me. Maybe I can do that by moving to choice functions. So a choice function, again, I'm going to do a theory of choice function that is very general. What I'm going to be talking about is I'm going to be talking about a set of options, and could be anything. For example, be the dogs again. And then I want to be thinking about if you give me some subset of these options. I'm now calling them options to distinguish with the things I had before, because it's kind of a different theory and I'll be connecting them. So if you give me some subset of these options, I want to know like which options do we choose from that subset. That's what I'm aiming to model here. And options could again be dogs, could be pizzas, could be vectors. But yeah, once more, let's go with pizzas because it's more fun than vectors. Good. So how do you model this? Choosing from a subset. A choice function does this as follows. It's very simple. Choice function is just a function that if you give it a set, gives you a subset that is chosen. Or you could also be thinking about ones that are not chosen, call those rejected, and that's then the rejection function that just returns you all the ones that are not chosen. And these are completely equivalent, so we can be talking about the one or the other. Every choice function has a rejection function, vice versa. So I'll be like using the two. Okay, and if we now want to talk about what it means to be chosen or what it means to be rejected, okay, I can focus on one of the two because I mean, they're completely related. So I will be focusing on the ones that are rejected. So I need to kind of tell you what that means to reject something. And I will be saying that that means something is rejected if one of the other things is preferred over that thing. So what does it mean if I reject pizza y from these three options right here? That means that there's one of these other pizzas that is better. So that means that either this pizza is better than Pizza Hawaii, or either this pizza meatballs here is better than Pizza Hawaii. So one of these two preferences is true. I think you see where I'm going here, right? I have here an or between preferences. So what I have is that this set of preferences here is desirable. At least one of these two preferences is true. And this okay, I can apply this generally. I can say that, look, I reject something if there's something else in the set that is preferred to it. That's what it means for me to be rejected. And at that point, I've established an equivalence between the choice function and sets of preferences. Integrate. And so, really, so this whole framework I had before, this particular instance where I was applying it to preference, in case you think, oh, it's a bit weird for me. Okay, if you don't like thinking about that, it's completely equivalent to thinking about choice functions or rejection functions. And this concept of I choose something from a set or rejecting from something from a set might be much more intuitive to you than, look, this is a set that this contains at least one desirable thing. Okay. So these three are equivalent, but that's great because for this thing, I already have a complete theory. So now I can add to that all the stuff I had before, and I find these equivalences. This was already equivalent to a set of strict partial orders. And now I've found, basically by my interpretation of choice functions, that this is equivalent to that. So choice functions are equivalent to sets of strict partial orders, which I think is very nice, because you can apply it to anything you like. Dogs, pizzas, gambles, but also, for example, you might apply this to probabilities. The thing that is desirable might be probability, or the thing that is desirable might, for example, be a horse lottery. If you like working with decision theory in that way, you can perfectly talk about these things as well. Okay, so that's that. This is this theory that I have, but what I didn't, okay, I promised you a number of things, right? I promised to introduce two tools, choice functions and desirability theory. I've done that. And then I promised that I would try and use those to talk about the meaning of imprecise probabilities and doing decisions with those and making independence assessment with those and so on and so forth. So that second thing I haven't done yet. So let me start with the decision making. Okay, there's a connection between choice functions and decision making is obvious. Choice functions, by definition, are objects that make decisions. They choose. But at this point, I've only established an equivalence with sets of strict partial orders. By no means do I have sets of probabilities here or admissibility or this kind of stuff. So to establish that connection, the first important insight is that making choices using a set of probabilities and admissibility is a particular instance of what I've been representing here. So it corresponds to the case where the options are gambles or utility functions or acts with utility functions, if you like. And then, okay, if for each of these probabilities, you consider the ordering that's obtained by ordering the gambles just with respect to their expected utility for that probability, so then you can transform a set of probabilities into a set of partial orders. And then the choice function that corresponds to that is exactly admissibility. That choice function is exactly doing admissibility for the set of probabilities. So it's a special instance of the theory I've been presenting. Okay, that's kind of not enough. It's a special instance, but I want to characterize exactly when I have that particular type of instance. To do that, to go the other way around, basically, I will use this theory of desirability and some extra axioms that I can now be using because I'm in this particular case. Good. So first axiom I'm imposing is this one. This is basically a translation in invariance. This one says that if you reject an option from a set of options, and then I translate both the option and all the elements in the set, then I'm still rejecting the translated option to basically the translated set. So this is something I could not do for pizzas, because I cannot add pizzas. But these are vectors, and so I can be like this plus makes sense stuff. So now I can impose that. Okay, and another way of looking at it, if you impose this, and by setting v here equal to minus u, or basically translating the option to the origin, if you like, then this is equivalent to saying that u is chosen from a set of options O, rejected from it, if and only if 0 is rejected from this set of differences right here. So this is imposing that when it comes, or equivalently, by our definition, that these things here, these preferences, so 0 is rejected, means one of these things is preferred to 0, means one of these preferences is desirable. So this set is desirable belongs to K. So you see that this axiom actually is saying that, look, when it comes to rejecting something from a set, it's only the relative difference that matters, and it's not the, and other than that, the meaning is the same. So, okay, what's nice here is I only have preferences over 0 here. I don't have preferences between two things. I only have one side and then always 0 on the other side. And this allows me to simplify things a little bit over the general thing I had before. Now I can just say that preferring something to 0 means it is desirable. And so instead of applying my whole theory to preferences over 0, I just apply it to these gambles themselves. Where the meaning is, if I find it desirable, it means I prefer it to 0. Okay? So now instead of working with sets, for example, preferences, in this context, I can work with just sets of desirable gambles, which is nice. Okay, good. So I've associated a set of desirable sets now with my rejection function or my choice function. Now I will be doing the regular theory I had before. I'll be imposing all these 4 actions I had before. And I will be building into my theory these 2 principles. Again, the same as before. If something never gives you a positive reward, it should not be desirable. And this here is basically an assumption of linear utility again. If some set of gambles is desirable, any finally positive linear combination of them should again be desirable. So I'm just applying the machinery I have to this for this particular instance. Okay, and to this I will now add 3 more axioms. The first is pretty straightforward and I think uncontroversial. It's a weaker version of what I had before. It says that if a gamble always gives you a positive reward and it's even uniformly bounded away from 0, then definitely that gamble you should always find desirable. It makes sense. Then the following one, the next one, this is an Archimedeanity condition. What this is essentially saying is that, okay, look, if a gamble is desirable, meaning if it's preferred to 0 in this case, then there should always be some tiny epsilon, such that if you subtract it from that gamble, then it's still desirable. This is what this is saying. At least one of these things is desirable, is this assessment. So there is, that means there is an epsilon such, and there is a u such that this thing here is preferred to 0. So that's an Archimedes, is basically a kind of continuity condition, but which several of you are familiar with. And then the final one, and this is the big one as far as I'm concerned, is the following condition. This condition says that if I give you a choice between 3 things, the first thing is some gamble that I've chosen, some bet that I've designed. The other one is the negation of the gamble, the opposite of that bet. And then the third one is pay me some small price. So I offer that you either this gamble, either this negation, either pay me some small price. Then this action, he says, you should never be paying that small price. That's what the action says. If you're fine with these actions, then you have this nice result, which is that the choice function satisfies this set of actions, if and only if there is a set of probabilities such that if you apply admissibility to it, you get exactly this choice function back. But that requires these actions right here. I think this is a very nice example of what you can do with choice functions, because it kind of moves the whole debate of should we be using sets of probabilities and then applying admissibility to it, to should we use, are we okay with these actions? And we can be discussing each of these actions separately and just like try and get to the bottom of what it is that we actually impose. And this cuts 2 ways. I mean, you can either like these actions, motivate them, and that provides you with a strong argument for doing this, for working with sets of probabilities and doing admissibility. Or you might not like some of these actions, and then that's an argument against this approach. I, for one, for example, I don't feel so comfortable with this one here. If you give me a gamble that you get to choose, and then I get to choose between that gamble, the opposite gamble, or I pay you 2 cents, I might very well, in some instances, just decide to give you 2 cents and be done with it. So I don't find it so convincing that I should never be choosing paying 2 cents. Just my opinion. Okay, so that for me, that makes me feel uneasy about working with sets of probabilities and doing admissibility for it. Okay, so one example of what you can do with the choice functions and this whole machinery. Another intriguing one, I haven't talked about independence yet. There's this condition, this extra axiom that we came across that in some slides that Teddy Seidenfeld at some point sent us. And he uses this axiom or this property to argue against the convexity of probabilities, and also that's why he sent the slides to us, to argue against the use of more general notions of independence, such as epistemic irrelevance and all these kind of things. And so he has this to kind of argue against those. And it's a very intriguing axiom. It's very intuitive. It's about whether or not information that you deem independent has any value. Let me quote. So when there's two events, E and F, and you deem these to be independent, not in the traditional mathematical sense, but just like in your mind, independent. Then the axiom said it's not reasonable to then spend resources to pay money, if you like, in order to use the state of one of these two, like whether E happens, to decide between two gambles that depend only on the other one. But mathematically, this looks as follows then. Consider a choice between three things. First, some gamble that only depends on the event F. Second, some other gamble, H, that also only depends on the event F. And then third, what's going on here, this is, okay, let's see if E happens. If E happens, I'm gambling according to G. If E does not happen, if the complement happens, I'm gambling according to H. And I'm paying epsilon to be able to do that. So the axiom then says that you should never choose the third option, because that one basically translates to I paid some money to make my choice between G and H depend on this event that I deemed to be independent. Good. I think this is a fairly intuitive condition. I found this intriguing. And Kat and I have been looking into the consequences of imposing this. And one of the consequences is if you add this axiom to all the previous ones, then you obtain the same result. So here we've added the axiom, but now we additionally have that for each of these representing probabilities, E and F are independent in the usual sense, as in like they factorize. Okay, so using this axiom, you can get to the usual notion. You can use that to motivate the usual notion of independence, complete independence, as in usual notion, but applied to every point in the set. There's, however, another thing that you can do with this axiom, and this one, when we first discovered it, blew our minds, I must say, the minds of Gert and I mean, that's the following. So what's going on? First, I've added one more axiom. This one says that I'm willing to bet both on and against the event E, provided that the odds are massively in my favor. So if you give me an odd on E, but massively in my favor, yes, I will do that against the same. So this I'm adding, but something has been removed here too. This goes up to E6. I've dropped E7. And E7 is the one I felt uneasy about. Is the one that says if you have a gamble, it's negation and pay me small amount of money. You should never pay the small amount of money. Is that one? It's the one I didn't like, and this one is gone. Okay. Now, if you do this, then the result says that if you only focus on decisions that are concerned with the event F, then for decisions involving that event, gambles on that event, then still you find that you are doing admissibility for a set of probabilities when you zoom in on that event. But this, I mean, let me make you understand why this blew our minds. I get to choose these events. So say that F is whether or not Teddy will have herring for breakfast tomorrow. Okay. And then I choose AE to be the outcome of some coin flip I'm doing here. So in my mind, those two feel pretty independent. And so I'm inclined to adopt this. If I believe that this captures independence, I'm inclined to adopt this one. Also, since E is me flipping a coin, I mean, a bet in favor of heads, if it's very much in my favor, I will say yes. And the opposite too, because it's just a coin. So those two make sense then. But then this implies that when it comes to making decisions about Teddy's breakfast, I should be using a set of probabilities and apply admissibility. But I can do this for anything, not just for Teddy's breakfast. I just need to imagine there's a coin flip that is, that I think is independent to it, and then this works. So this is a super strong argument in favor of sets of probabilities and using admissibility. And this blew my mind because I've just proven that this is equivalent to this other axiom, this one that I don't like, to this one that f minus f, and then paying some, and this one. So as Katja would say, luckily, this conflict in my mind got resolved by the following observation. This axiom right here, you can rewrite that using this translation axiom. So which said that if you make a choice from a set and you translate them all, then nothing happens. So what I've done here, I've subtracted from all of them these first two terms here. So here I get the minus epsilon, and then here, okay, this takes a bit of fiddling around, but if you subtract these two from that, then you get this one. If you subtract these two from that, you get this, and again, you get left with minus epsilon. So this under axiom E0 is completely equivalent. But now you see that actually these gambles G and H individually don't matter. All that appears here is their difference. That's all that's really substantial to the axiom. So let's just like denote this difference with F. And now look again at this axiom here. It now says, if you have three options, and the one is, let's look if E happens. Let's look at if the coin flip lands tails. If it does, if it lands tails, I'll you take the gamble F. If the coin flip lands heads, you take the gamble minus F. I get to choose F, by the way. Or you pay me a small amount of money. Now this kind of sounded intuitive. This one, not so much. This very much feels like this other thing. Now I'm no longer surprised that it implies this axiom I didn't like, because it very much looks like the axiom I didn't like. So you're actually kind of imposing that hidden in here. And so at this point, this kind of put my mind at ease, because there's no conflict between these two results. But it also means it has a unfortunate consequence. It means that if you want to use sets of probabilities, and then you want to apply admissibility, use admissibility with that, or you want to do complete independence, like the usual notion of independence, it implies that if you want to do that, you need to be fine with imposing these axioms. You need to be fine with this whole paying a small amount of money you shouldn't do that. And I feel uneasy about that. And for that reason, I also feel uneasy about using admissibility, sets of probabilities, and so on. So I leave this open. It's up to you with how you feel about it. But if you feel uneasy about this too, then okay, let this be an invitation to consider looking at some of the alternatives that are out there, at other types of imprecise probability models, at other ways of using sets of probabilities, at other notions of independence, at other notions of decision making. And okay, if you're interested in those, or you want to know more about them, or more on imprecise probabilities in general, then good starting point might be the Society for Imprecise Probabilities. So we organize some events, very nice events, I would say. We also have lots of information on imprecise probabilities and pointers to information on the website. We have a mailing list. So you're most welcome to join. Just go visit zikta.org. And that would be it for me. If there's any questions, I'm very happy to take them. I have to get my drink there.
Yes.
Quite close.
So once again, if you have a question and you're joining us remotely, please just pop a Q into the chat. And Seamus will kick us.
So I'm just wondering about the various other sorts of axioms that people think about in choice functions.
Yes.
Things about if you I can't remember which of them you had in your first few axioms, but things like sends alpha and
The ones
sends
for
beta.
pizza, you mean, or?
No, so the axioms for choice functions.
Well, okay, I haven't given in the general
Oh, yeah,
context
okay.
actions for choice functions, but then due to this relation between sets without sets
I
and
see.
choice functions, any axiom I had
Yeah.
for sets of desirable sets of things, I can immediately translate to a corresponding one for choice functions.
Right.
But okay, I didn't give
Let,
those.
let me put it this way then. So which of the axioms are, things like sends, alpha or beta conditions, or, path independence, or the various things that people talk about in the literature of choice function, which of those are consequences of this framework? Which of those are might be interesting things to explore adding to the framework? Oh, that's quite an open-ended question.
Yeah. Okay. In my view, all those conditions you're talking about there, they kind of initiated just from thinking like, oh, this I might like.
Yeah.
But then if you start working with those, it's a mess. So you start piecing these together, but they're very much not built for doing this kind of stuff. And so at some point kind of just suddenly moved away from those. And I was like, no, let's look at the actions that are actually needed to get this stuff going. And then we came up with those. Now,
I still feel like they are nice to have, though.
No,
Like, it would be
okay,
nice to have them.
okay, I don't know which you're all talking about,
Yeah.
but many of them are implied
Okay.
by this. So
That's what I
like,
thought,
all this
yeah.
sense alpha. So these things are, many of them are in there or in there for particular cases. And so as to which ones exactly, which case, I mean, I don't want to comment on that too much because that might go wrong. I haven't really went into that into detail. But definitely, I think Arthur at some point looked at how, at least for the case of gambles, these other axioms, kind of how they relate in his thesis. There's some of these connections. And
So, not so bad. So alpha is implied, huh?
I think so. Yes.
Alpha, yes.
Next we have Arthur. Yes.
But I'm happy for Arne to go first.
No.
Sure. I have a small question.
Yes.
Does E6 and E7, does it imply mixing this? Or what? Or are your E-admissible choice functions are mixing? No?
Okay. Yes. E-admissible choice functions are mixing. That's true. But these two together don't apply. The Archimedes. Okay. Are you willing to also have all the others?
Yes, sure.
If you have them all, then yes.
Yeah.
Because it's e-admissibility, and e-admissibility is mixing. But mixing this as a thing on its own is not in this list. And the reason is that this one is strictly weaker than mixing this. And that one is all that I need to get to e-admissibility. Mixing this is actually too strong an axiom to get to e-admissibility. You can do that because eventually you get it for free then, but it's too strong an action to actually, and I prefer in these kind of representation theorems the more simple ones. If you want to think about why it's strictly weaker, and so this assessment here, if you think about it in the terms of the case, that means u plus epsilon and minus u plus epsilon, so that's doubleton, is desirable. So one of these two should be desirable. U plus epsilon and minus u plus epsilon. One of these two should be desirable. That's equivalent to this action. And then if you know what mixing is, you see where it's coming from, because a convex combination of those two, or just like adding them, gives you twice epsilon or epsilon. And that, just epsilon itself should always be desirable. And hence the mixing this action would then say that the original thing that you kind of mixed should also be desirable. And so for that, this is just one particular instance of applying mixing this. That's enough. It's all we need to arrive at e-admissibility. All the extra stuff from mixing this, okay, will be implied by all of those, but I find it less intuitive to think about. I prefer focusing on the simple one because it kind of captures, I think, more clearly what's going on.
I think that's really nice.
Thanks.
There's a question online from Arne.
Sure.
Arne, are you willing to explain?
Can we open the grid of people so we can see them?
Arne is muted.
Okay. So I was asking about your uneasy feeling about the axiom E7. If the
Yes.
E0, like you can do weird stuff with E0, I think. And would you feel just as?
Sorry, can we bring the volume up? Because
We need to do
I
it.
do. I need to do this myself. Okay.
Sorry.
Could you repeat it, Arne? The
So
volume was quite low around here.
Isn't your uneasy feeling coming from from E7 coming from E0? Because you can also restate it as f minus epsilon is not in the choice function of 0, f minus epsilon, and 2f. And I think that's that you then would say, yes, that's reasonable, or am I...
well, because I know it's equivalent to the other one. No. The whole thing, the point that if you endorse sets of probabilities and admissibility, it implies this remains standing, and I don't like this. So in that sense, I mean, this is a consequence of doing that, and I don't like the consequence. But fair enough. I mean, this is just like what happened with the independence criterion of Teddy that I said. It's true that if you like transform them a bit, it can, like the intuitive feeling you get from them can be very different. With the case of Teddy's example, I mean, the one version I found convincing, and then only after I transformed it, no longer found it convincing. And okay, fair enough. There might be transformations in here that I feel less uneasy about, but knowing its equivalent is still an issue for me. But you're right. Say that we, for example, drop E0, then this whole thing about them all being equivalent is gone. And so indeed, a theory that doesn't have E0 but does have a different version of E7, that I might feel less uneasy with. Agree. But okay, there will not be admissibility for sets of probabilities, because for those they are definitely equivalent. So with dropping E0 and then having Teddy's action, that okay, I might feel better about it.
Okay, I think Teddy has a follow-up, and then Kevin has a follow-up.
Yeah, Teddy, would you like to read out, or like talk about what you wrote in the chat?
So I'm a bit concerned that there are rival sense of desirability being used in comparing e-admissibility with what you're doing. To the extent that I understand preference in connection with e-admissibility, it's trivial to have a little example where 3 options A, B, C, and B is uniquely rejected in the triple, but neither A nor B is strictly preferred to C. That is, I don't find A desirable to C, nor do I find B desirable to C.
Yes.
But I thought your sense of desirability would not support that interpretation.
It does. It does. The thing is that what you think about is one preference ordering, and then you can indeed not capture the stuff you're saying. But this theory is equivalent to sets of preference orders, and that is what allows you. So there's not just this one order, and I have some preference and some not. That would be the simple model in my theory. I'm looking at depending on which side you take, either sets of these preference orderings, either sets of desirable sets of preferences. I mean, that's the whole equivalence thing. But it's so the point is that you get this disjunction between preference statements. This is a power you don't have if you just work with preference in the usual sense. In my theory, you can say, look, I have this preference, or I have this preference, but I'm not stating, I don't know which of the two. I'm only stating it's one of these two. And this, if you just work with an ordering, you cannot do that. That would be the simple type of model. But you can do this if you work in a more complex version. And so that's why this behavior describing can be captured with desirability, provided that you don't understand desirability as sets of desirable things, but that you consider the more general theory that also includes this disjunction.
So I
So
think
that
now
answers your
it's
question?
just a terminological notion that in e-admissibility, there's an account of desirability with a single strict partial order, and you want to use desirability without such a notion, if I understand correctly.
Yeah, it's basically sets admissibility is just a bunch of partial orders, one for every probability measure. So that, and if you think about it that way, it makes perfect sense that, I mean, this connection between preference and admissibility is in its simplest form just that. I mean, admissibility is dealing with a bunch of preference orders, a bunch of preferences that are corresponding each to different probabilities. So if you use a collection of those, that, I mean, then it thinks is straightforward to see that this is the connection. But if you want to use just one, no, that's not going to work.
Yeah. Okay, cool. So I also had a follow-up that I wanted to ask. Oh, I guess I should. Yeah. All right. My sense of this, like, you know, whenever you have u minus u and then some small minus epsilon, it's always like minus epsilon should always be rejected. This feels to me like an anti-risk aversion constraint, right? So sort of in particular, what it's saying is that it's never rational to prefer a sure small loss, even against, right, potentially enormous, like uncertain losses and gains, right? So like, I mean, you could be like plus a billion, minus a billion on a coin flip. And it's irrational for me, potentially like losing everything, or, you know, maybe getting unimaginable riches. And so I think, right, rather than sort of reading it as like a sort of problem for sets of probability functions or something, I think that that intuition to me is suggesting that, okay, if you like those kinds of intuitions, then maybe you really don't want any kind of expected utility account. And so, you know, given that e-admissibility is a kind of expected utility account, right? That this kind of, right, and because it's not a function of the utilities, right? It's supposed to be like, actually, you can even like put the gamble in utils, right? And you still just think that some kinds of like risks you're still just like not willing to take.
Yeah, agree. So there's a need, there's two aspects to it. If you have these things, if I was losing lots of money, then this will make you feel very uneasy about this action, but that's not fair because you're assuming the utility in this thing. So that's not it. It's about feeling uneasy with it, even without that.
Right.
If you paid out in utilities or probability currency or whatever you like, feeling uneasy about it still. As for the linear utility itself, that's a different matter. This is in using this closure operator right here. Now, you could change this too, right? That's the power of this whole general theory. I don't need to do posy. I can, for example, take a convex hull. If you don't feel like scaling, if you think, or you just want to scale down and not up, for example, that makes perfect sense for some kind of thoughts on utility. No problem. You just put a different closure operator that doesn't do that. So this you can do, or you can apply the whole thing to horse lotteries, and then, okay, you also solve, like, you can do very powerful things with more complex types of utilities right there, right? So that's not this one. This is really the linear utility to me is here, and then arguably maybe also here. This I find a little bit more difficult, but to me this feels like also related to linear utility. Doing this.
Yeah, I just wanted to resist the suggestion of the talk, right? That this is sort of showing like, oh, like this is a problem for like thinking about sets of probabilities, and thus a reason to not think in terms of sets of probabilities. Like it seems like the real problem, right, is the like thinking that
you mean doing that, but for fixed utilities might be the problem.
Yeah, for committing yourself to expected utility maximization being sufficient, right? Because like that's going to be a case, right, where like, no, I mean, like the expected utility there clearly of like losing a cent for certain is worse, right, than one of the two gambles.
You feel that it's really linear utility, you don't feel uneasy with it?
Even
it's a more difficult question.
Even if it's linear in utility, right? I mean, so if like the two things are like, right, like lose my house, right, or you know, like some really amazingly bad outcome and some really good outcome on a coin flip, right? 50-50 chance of each. And I have to say, okay, I'm committed to either pick heads or tails, or I can pay a cent to opt out. I'm quite happy to pay the cent.
Yeah, and also the whole centing really does it for me. Yeah. Although maybe also there's a hidden inside some utility aspect because this cent is kind of negligible, and there maybe I'm also.
But it's for any epsilon though, right? It's supposed to be negligible.
Yeah, but okay, it's for the small ones that it's really the power is in the action, right? I mean, for very big epsilon, yeah, sure, I won't be choosing
Of
it.
course,
I mean,
right,
it's the fact that that you should do this for very small epsilon. That's where really what it's really about.
But you're not, like, this judgment doesn't require you to reject negative epsilon from either the pair of you, negative epsilon, or the pair.
No, that's right. Yeah.
So I don't, but I mean, the description of the case is like, well, I would be uncomfortable doing either of those, but that's different than being uncomfortable doing this. And I don't like, when this is, and this sort of harkens back to the discussion at the table yesterday, like, if we were thinking about like a particular instance where I'm going to reject an option and then somehow nature is going to resolve this and I'm going to end up with one of the two.
No, I say,
But as
it's saying I cannot choose that.
Yeah. If this is just,
You're not allowed to say I'll pay the epsilon.
It's you're
It's like that.
you're required to either pick one or say, okay, like I know one of them is desirable.
I know, but just as capturing my judgments of desirability, I don't get why to feel uncomfortable with this.
Well,
Like,
this
of course,
totally-
one
this
of the
totally-
two is desirable, is preferable to negative epsilon. It's just a matter of logic that if this is paying out in utility,
Okay.
what?
To me, not, but I think that's the whole beauty of the whole approach, is that it gets you to kind of reduce the whole discussion to this kind of very point, how you feel about this.
I mean, I agree. Like, if you're giving me this option, it's like some crazy coin flip with my life, and then I'm gonna reject negative 1p and give it to Arthur, and he's gonna somehow resolve it. Like, I'm gonna be unhappy with either way of him resolving it. But that's because I'm unhappy. Like, because I misdescribed. Well,
no, the point is you should be including the minus epsilon. So it's irrational to allow Arthur even to do that. So that's different from
but
what
I think
you're
we're
saying.
misdescribing the choice. Like, this is not the.
No, well, fair enough. I mean, I
Anyway,
was hoping to
sorry.
initiate this kind of stuff. But
Just a small suggestion. Didactic, I think, if you just replace the epsilon by 1, it's a simpler version of the axiom, and I think it's more telling.
Smart.
fair enough. Under the linear utility.
Yeah, well, yeah, that's there anyway, right? So, yeah.
But I'm not sure this will be equivalent though.
I can.
Wait, oh no, sorry, no, this one is not. Here
multiply-
here it wouldn't be, but here it
Yeah.
is. Sorry,
Yeah,
my bad,
multiply
my bad.
anything
No,
by-
it is.
Divide everything by epsilon,
Yes.
replace u epsilon, yeah.
But you should be careful with this really, because for example, here you cannot do that.
Yeah.
So it's like tricky business. No, you're right.
I have a comment, but I don't want to usurp it.
No, there's no one's in the queue.
Yeah, I was really intrigued by the making the objects anything, and in particular, possibly preference orderings, and then potentially extracting some structural properties that the underlying preference orderings might have. I mean, this strikes me as really similar in spirit to what we're aiming to do, except we're going about it slightly differently. So to be able to talk about preferences, making the objects of preferences. Instead, we're doing some like serious work thinking about what makes these things valuable in a world, so that for each preference ordering, we can associate it with a gamble, and then just ask questions like, well, say I have a vacuous model, like
Over the orderings.
over the orderings, given the theory of value, what does that tell me about which models I should prefer to the other ones. And that's sort of what a dominance argument in epistemic utility theory is. It's saying you should, you always prefer some kind of coherent model to an incoherent one because it dominates it in utility.
Yeah.
So even if you were vacuous, you should prefer that one to another. But there are a lot of the substantive work is trying to give a utility scale for these things, where that kind of captures something related to accuracy. But one obvious kind of, like when you're doing this in an IP context, the limitations of working with real valued utility sort of hit you in the face pretty quickly, and you don't require that. And then there's a trade-off, how much you're building into the preferences over the preferences. That's a substantive commitment. Here you're putting substantive commitments into the utility function.
The things could
but it
also
strikes me
be
like
entire preference ordering, by the way. But
the things that you're.
the things could also be entire preference orderings, if you like.
Yeah, no, I mean that's
But okay,
the objects of
so,
the objects that you're.
Yeah.
The option sets. Yeah, I mean, but that's what we're.
but okay, at that point, it just becomes maybe funny as well. The network machine maybe uses power because how you need the closure for this kind of thing.
Yeah. Anyway,
Oh.
I wanted to sort of suggest that whether or not you like it, you're sort of on team other.
Okay.
Yeah.
I definitely don't reject.
Good.
Are there any other questions?
Not at the moment.
So
in the queue.
something I might like to add is I've been reading some of this work of Ketchum, and what's nice, but which I didn't talk about here, is that you can do all of this stuff also for filters. So you can generalize. The only thing that changes is where is it? Is this one. Here, there's a possibly infinite. Sorry. Here we are. There's a possible. Here, this is for 2, and I did the inference. But this axiom says that you can do this for an infinite number of things, and then do all possible selections, which is an infinite amount of selections, and then do the whole thing. If you restrict here to finite number of things, then the whole thing still works, but you get filters instead of sets. But so this the representation, this still works, but it's no longer really one set that represents it, but a whole filter of sets. Basically, by extending the idea in the paper, but with general closure operator, because it doesn't really depend on that. So just like taught to without that.
Excellent. Cool. That brings us exactly to time. So let's thank our speaker.